form, and then you check to see if it is going to be a valid argument. Most of the time you need a table, or sometimes you may get some property and just do it briefly if you like. So this is going to be practice. Okay, that's going to be practice test number 1, and that's question number 1. We want to check if the argument is going to be valid. So this is the number 1 that we are going to consider. Okay, this is the case determined. So if I work, I cannot study. So it's going to be one case. Either I study or I pass mathematics. I work, therefore I pass math. So what we're going to do, we are going to label this information one by one, and then you put them together. Okay, so this is how it's going to go in. So if I work, I'm going to get this one to be P, then, so I write it down here, what I'm going to do. Okay, so I suppose, we can do it on your version that you have label it, but since I don't have it, I want just to explain it. So the P is going to be I work. Okay, this is going to be the P, and the Q, I take the Q to be I can study. Okay, I can study. Then I need another one. I take the R, is going to be I pass. Okay, I pass mathematics. You can identify it right on that question that you have. Now you put them together. So the line of the argument is going to be the first part. If I work, I cannot study. So it's going to be if P implies not Q. Okay, the second part is either I study or I pass math. Okay, study would be Q, or passing math is going to be R. And the conclusion is going to be, therefore, I pass mathematics. So this means this is it. Implies R. Okay, you have to write it down for us. You get points for each of them. Just change it to the symbolic form. Now you want to check if this is going to be a valid argument. You know that this argument is going to be valid. Okay, this argument is going to be valid if, so this is what you have to check. You check to see if the first implication, that's the first one, and the second one would be Q or R. That should imply R as a tautology. So this means if you draw a table, your table must be true all the time. Some of them can be done algebraically, but the safest one is the table. So what we're going to do, you need a table to confirm it. So that's what I need. I need a P here. This is going to be PQR, because we have 3 variables if you like. Then I need the not Q. That's going to be the not Q. Then I need to form if P implies a not Q. Okay, then I need a Q and Q or R. Q or R. Then I need to put them together. It's going to be P not Q. Okay, and Q or R. And then the final part. So the final part, I don't have any room, so I'm going to call it Q. So this is going to be what I call Q. If you have room, you can rewrite it. So you have to prove that all of them are going to be, a tautology. Okay, you try, that 3 variables, 3 cases, so it's going to be true, true. Okay, this is going to be true, true. So in this case, this is going to be false. You start with the true, then we get to the false. This is false. And that make this one into the false. So the result is always true. You don't have to continue. Okay, that's easy, of course. This is also true, but you save sometimes. Then you just consider various cases, true, true, that give you false. Okay, this is going to be true. So this is going to be true. Q or R is going to be true. Okay, this is true and the R is false. So this means sorry, this portion over here. So we get a true, true. This is going to be true. Okay, this is going to be true. And then implies R, and R is going to be what I take. I take the true, true, false. Okay. Let me just double check it because it's the way I direct down is different. So that's going to be true, true, false. So in this case, not Q is going to be false. Sorry, not Q would be false. Okay, not Q would be false. So this is again false, and I don't have to continue. So the result is going to be true again. Okay, and then you continue. It's going to be a tautology. So true, false, true. True, false, true, that give you true. So this is going to be true. And Q or R would be true. And the R is also true. So this is going to be true. Then you get false, true, true. False, true, true. This is going to be false. So this is false. You don't have to continue. So that's going to be true. Because when it's a false, this would be false. And if you start with a false, you get the true all the time. Okay, and then you just keep going. So this is going to be, next one's going to be true, false, false. Okay, so this is going to be true. So this is true. But Q and R, both of them are false. So this would be false. The result would be true. Okay, and the other cases 1, 2, 3, 4, 5. The other one that I consider is going to be false. Okay, false, true, false. False, true, false. This would be false. So you get a false, false. This is going to be true. And Q or R, in this case, this is going to be true. And the R is false. Where is this one? I get the false, true, false. False, true, false. So the not Q would be false. And over here, this would be true. Q or R, this is going to be true. Okay. So this would be true. And the R is false, probably. This is one of my assumptions must be wrong. Okay, so I start with the true, false, false. This is going to be false, true, false. Okay, so the not Q would be, the not Q would be false. So I start with the false, this is going to be true. So I have Q or R, Q or R. It would be true. So both of them are going to be true here. Okay, and we get to the R, R is false. Must be something wrong with this one. I'm not sure about it. Any suggestion? Did I miss anything? All of them must be true. So I check it again. Didn't have this one before. So false, true, false. So the not Q would be, the not Q would be false here. Okay. So P is false and the not Q is false. So this is going to be true. So Q or R, Q or R over here is going to be true. So the combination of these two would be true. And then you resulted to the R false.
On the practice test, you had a third premise of P, and that works out correctly.
Which one?
On the practice test, you have a third premise of P, and then it works out correctly.
Oh, yes, I missed one of them. Yes, that's one, sorry. Yes, you are right. You have another one here. That's one. Sorry, I have another one. P here. Yes. So it's a P implies a not Q implies Q, or R implies P. So I have a P, that's it. So that would be, yeah, I missed one of them. The P is here, everything else would be the same. But anyway, if you check the other ones, it's going to be true all the time. So that's a false, true, false. Yes, I missed one of them, sorry. But it's not going to be affect any others. Okay, so if you check all these, they are going to be again. So this is going to be true, Q or R would be true, true, did you get a fall? True. And I'll give you a shortcut in a minute, but false, false, false. And that's going to be true, true, false, true, and the true. It's going to be a tautology to get these numbers. Okay, so this implication over here, I missed there was another one. Yes, I missed that one, sorry. So basically this is what we proved, and Q or R and P implies R. So it's going to be a valid argument. Okay, it is a valid argument. When it's a two variable, it's easier. But when it's going to be three, it takes a little bit more time to do it. But you can do this one in a short form. But you know, but the table is going to be okay. The table is going to be fine. But sometimes it would be easier. You know, you can try if you like. But the table is fine. But if you want a second method, do you want to try it? You see the second method? The crucial part of the second method, remember, was that idea that we can, you see, I just remind you again, that's a crucial part of the second method. The fact that if P then Q is going to be equivalent to what? Equivalent to the
Not P or Q.
not P or Q. That's the key. So if you have these type of ideas, you see, these are going to be quickly, you can put them together and that take care of it. So for example, you can start with the if P not Q, that's given to you. So this would be equivalent to what? It's going to be equivalent to the not P, okay? Equivalent to the, that's it, equivalent to the not P. Then we have a not Q, if you like, okay? So it's going to be, I have the, yeah, this is going to be the case. You can go with this one, or you can change this one. Maybe that's easier to change it. Okay, just show you. It's option. It's nice. You see this? Look at this one. This would be equivalent to what? And this is going to be equivalent. I need a not here, so I change this one into the not Q or R. So now it is going to be equivalent to what? It's going to be equivalent to the not Q implies R. You see? Not Q implies R. Now put them together. What do you have over here? You see? Now you have the P implies a not Q, and you have that the not Q implies R. Remember that transitional one that we talked about it? You drop the not Q, so this is going to be equivalent to the P implies R. So what I did, I combined the first two. You see, I combined the first two. So what we are going to have now is the first two combined to the if P R and the P. If you give me P, I give you the R. I've already given you the P, so I have the R. You see, I have the R. And that gives you the result right away. So look at this one that you want to prove. You want to prove if P not Q and the Q or R, and the P implies the R. So you can try it, especially when this or combination or the implication one. But anyway, otherwise the table is going to be, we give you one of these, it's going to be, a couple of them are going to be just the one that we did before, that would be can be easily changed. But the one that you have, a couple of more variables is not bad to get through this one. Okay, so that's going to be the first one. Any question?
I have a quick question.
Yes.
In the truth tables in the second to last column,
Yeah.
For P implies not Q and Q and R.
Yeah, there is a P also here.
Oh, there's also a P.
Yeah, I missed the
Okay.
P. Yeah, that was why
Probably, yeah, that's probably
yeah,
okay. Thank you.
yeah, I missed that P. Okay, so let's quickly give you this. The one over here is in different order. You have the best. You have the not complicated really, a little bit more involved one first. That's okay. So we want to give you something to practice. So let's take the second one. The second one. What is the second one? The second one, if I take the bus or I walk, okay, that's one. The second one, I take the bus or I walk, P or Q, so I write it down to see what I'm going to change it. So let's see what I need for this one. So I take the P to be, the P to be I walk, I take the bus. Okay, you just identify it on the question, you don't mind, okay. So I take the bus, this is going to be P. I walk, so I need a Q. I walk. Okay, then I get tired. I get tired. I get tired. Okay, so this is now what you want. And the first step is I take the bus or I walk. Bus or I walk, so it's going to be, and this is it. It's going to be P or Q. That's the first part. The second one is going to be I walk, I get tired. I walk, therefore I get tired. Okay, and we have another one. The other one is I don't get tired, so not R. Okay, therefore I take the bus. I take the bus would be P. Okay, that's the implication they're going to have. Again, you see that's the best candidate for the shortcut, but so what you have to prove is this one, if P or Q, that's safe, is proof, and not R implies P as a, okay, implies P as a tautology, if you like. Okay, then you draw the table and just say this is going to be true. It's going to be a valid, a valid argument. So just the same table. You can go ahead and do it. It's going to be PQ, and that's going to be, that's it. You need a PQR. So they're going to PQR. You need the negation of the R. Then you are going to form a P or Q. Okay, Q or R, Q, then R. And we have the negation. So you put them together if P or Q and Q implies R and not R. Okay, and the Q, the result. To get those numbers. Okay, and just quickly just get those 8 cases and just put them together. Okay, it's going to be true, true, true. This is going to be false. Okay, as soon as you get the false here, you see this would be false. So this result is true. Then we get to another one. Another one is going to be true, 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 false. Okay, so this is going to be true. So this two is going to be, we get the true here. So we start with the true state Q. True to get to the false, so that make this one into false. Okay, since this is false, this would be false. The result is true. Don't have to continue. Okay. So then the other one is going to be, let's have true, false, true. Okay, true, false, true is going to be, this would be false. So you don't have to continue because make this one into false and this would be true. Okay, the other case is going to be false, true, true. Okay, we get the false, true, true. Again, this make this one into false. So this would be false and the result is true. Okay, and so we get the false, false, false. So we go with the what? We go with the true, 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 false, false. True, false, false. This would be true, but we get the P or Q. P or Q would be true. Then Q, then R. Q, then R is going to be true. So everything is true. So on the other side, P is also true. So this would be true. Okay, so the other case that we have is going to be what? Is going to be false, true, false. False, true, false. That give us true here. But QR, Q is true, R is false. So that make it to the false. So we don't have to continue. That give us, because this would be false. Okay, and what else? We got the false, false, true, false, false, true. So this would be false. So that makes this one into false, and that would be true. And I think that's the last one that we have is false, false, false. So in this case, this is going to be true, and this is false. You don't have to continue because that makes this one into the false and the true. So it's a valid argument. See, quickly summarize the cases that it's going to be true. So it is a valid argument. With that, okay. Any question? So again, you can, if you like algebra, you can change this. The way I did it, I just changed this one into the method 2, the algebra one. I changed this P or Q. I like to change it to the implication. I need a not P here, so it's a not P or Q. So now that give me a not P implies Q. Okay, in this format, not P implies Q. So if you check, this is not PQ, and I have a QR here. You see the second part? So I could combine them together. I have a not P, then Q. That's the first part. And in the second part, I have Q implies R. So the middle one would drop. So that gave me a not P implies R. Okay, so I combine the second, both of them. So what I have a not P implies R and simply not R. Okay, this is what I have. I want to get the P. So this is going to be the same as what? Remember, use the contrapositive of this one. This would be the same as a not R implies not P, which is a P. You see not P. And this is a not R. So that give you not R implies P and the not R. So you give me not R, I give you P. I've already given you not R, so you give me P. You see? And that gives you the result right away. That's the option, but the table is safe. You get one of them, you don't have time, but but it's good to know for future. You may have to apply this one for some sort of programming somewhere. So it will help you quickly to take care of it. Okay, so these are the one with the 3 variables question. We give you one of these, either directly we ask you to prove something for us or in the course of these. The other one is going to be with 2 variables. So let's check one of those 2 questions. So be patient. It's not difficult. So the type 2 or the type 1 really, we could have talked about this one first, is going to be the next one, which is a number 3. So I just show you what it is, and then I organize it. If my congressman is crazy, he likes Washington, my congressman likes Washington. So the two famous cases, that 2 other famous cases that we're going to have. Okay, so I manage it in this format. So I need a P is going to be, so suppose B is the fact that my Congress, again, you just identify it, accept it. My congressman is crazy. So that's going to be the P. So I pick the Q is that he likes Washington. Okay, he likes Washington. So that's going to be Q. I don't need anything else. So the first expression is that my congressman is crazy, so he likes Washington. So this is it. It's going to be if P, okay, if P then Q. Okay, if P then Q. And the second part is that he likes Washington. Okay, he likes Washington. This means Q. Okay, this means Q, and then the conclusion is going to be, therefore, he must be crazy. Okay, so this means P over here. Okay, everything's all right. So if he's crazy, that's a P. If he's crazy, he likes Washington. That's the one. The second part, he likes Washington, which is going to be Q. Okay, therefore he must be crazy. Okay, you know, if you just think about it, you see, if you give me P, I give you Q. I give you Q. That would implies P. So it's a kind of converse version, if you like. So you must be, you know, you must have some suspicion about this one, that this, if this can be true, okay. You know, it's a converse. It's not the case that the converse is always true. So you guess that this must be a false one. So what you can do is you can quickly reject it, or just get the table and show that one of the column is false, okay. So the question is going to be, if I give you P, then you give me Q, okay. I give you Q. So does it implies that I get the P? Means if this converse is true, so which is not. So you can reject it by drawing the table as usual, complete it to get it, or just find the one that you like. Okay, so I need a P and the Q here, P and the Q. So we need only P then Q. Okay, P then Q. And if P then Q and the Q, okay, and the result, if you like, okay, the result, which is going to be, this is it, if P, or just call it Q, the result. You see, you can check to complete the table, or just think about it. Think about it that you need something to be false here. Okay, in order to get the false, you need the first implication to be true, the second one to be false. So you have to pick to be false. You have to pick this to be false. Okay, you may try false and true. Okay, false and true. So there you are. You start with the false statement. Of course, this is going to be true. Okay, and this is it. So this is true and this is true. So this is going to be true. Okay, there you are. So the first one is true. The second part is false. So the last part is false. So you don't need to continue anymore. Okay, even if you continue, you will get it. Okay, but you don't have to complete the table when you are going to reject it. Okay, so the argument is not valid. So it is invalid. It is not a valid argument. Okay, valid argument. Any question? So, you can see that this is not going to be the case, but you draw your table. If you missed it, you may have to go a couple of cases. Okay, if you take both of them to be false, the result would be true. So you go one more to get the false. Okay, any question? So these are the one that you should be able to take care of it quickly. Just kind of a converse. The other one is remember we talked about the inverse error. So we should have one with the inverse error. I think number 4 would give you that one. Okay, so we go with number 4. Are you ready for number 4? Number 4, the argument is this one. We did similar one before. This is it. Mary wearing green socks. She has passed algebra. She's having on something with different color. So unfortunately, she failed algebra. So put them together. So we need two variables only. So this is it. So you are going to suppose that P is going to be the fact that she's wearing, Mary is, she's wearing green socks. So that's the first part. So that's a P, and you need a Q. Q is she has passed algebra. Okay, she has passed the algebra. So that's all we need. So the argument now would be changed. The first part, she wearing green socks, she passed algebra. So the first part would be if P then Q. Okay. And the second part, she got a blue one. So she got a blue one means she are not going to have the green one. So that would be a not P. Okay, not P. And the implication that they are looking for is, unfortunately, she failed algebra. Okay, that's what we want. She failed the algebra means she's not passing the algebra. So that's going to be not Q. Okay, if you look at it, you know that if P then Q is equivalent to what? Not Q implies not P. Not Q implies not P. That was a contrapositive. But this is a kind of inverse. You see the inverse of if P then Q. The inverse was what? The inverse was not P implies not Q. But we talk about it, that inverse is not true all the time. Okay, so that's the case that you should be able to reject it right away. Okay, so if it was if P then Q, if it was not Q, that would imply not P by the contrapositive. But this is not the case that if P then Q is going to be, P then Q is not equivalent to the not P, implies not Q. Okay, so it's invalid, so you can reject it right away. But just get the table, and in your book they refer to it as a inverse error. Okay, inverse error, and they consider it. We can accept that one too, but it's not bad. Just give us really a little bit of the table. But if you want to go with your book, if you just identify that that's going to be the case, we accept it. Okay, we accept it. But if you want to be complete, if you like, this is the one. Bad, even if you identify it, I accept it. And not bad. Oh, I'm sorry. So what we want to do is we want to check if P then Q and okay, not P implies not Q as a tautology. Okay, we want to check if it's going to be true. So we need a P and the Q. P and the Q. Then you need if P then Q. Okay, then you need a not P and you need a not Q. Okay, then you have to form if P then Q and not P and the conclusion. Okay, so again you want to reject it. So since you want to reject it, you want this to be false, and the implication is false. If this is true, this is false. So you want the not Q to be false, so your Q must be true. So So you get this one to be true. This is the other one to be false. You get it right away. Okay, going from the false that give you true. And not P here is going to be true. So what we have over here, you see, if P then Q is true, but then not P is also true, so it's going to be true. So this is going to be true, but this is false. True, false, that give you false. Okay, that's it. So this so show that the argument is not valid. The argument is invalid. Any question? So that's going to be no, and that is going to be the case. Or the expression, as I told you, is I think is the I call it the inverse error or something, you know, by the inverse. I think that's the expression by the inverse error. The argument is invalid. That's a property that's, you know, in your book, but you have to write it down to show that this is related to the inverse. Okay, you cannot say just by the inverse error the argument is invalid. You have to show that. You see, no, we show it. We see that inverse, because this is if P then Q, they want a not P implies not Q. Not P implies not Q is the inverse of the given argument. So it's not the case that always the inverse of a statement is also true. Okay, so that's why we got it. But it's nice to give a counterexample. We got it. Okay, that's a better way to write it down. You see, so play it safe. That's it. That is the valid argument. Any question? And we just give you another one. That number 5. In number 5, we give you the statement and we ask you to prove it. Okay, so you have to use the table to get these numbers. Okay, you can do with the table to take care of it, and I think both of them are true for number 5. But we prefer to give you not to give you kind of a statement type like 5. You can try it. It's nice to get the table, and it can be done by algebra quickly. That number 5. If I get time, I come back and show the algebra part. But we would like to give you something that you translate it for us. Okay, you build up the problem yourself. But you can practice those two. So if I get time, I come back and show you not the table, just the algebra part. It takes time. You have 3 variables P, Q, R. Okay, any question? So that's topic of the valid argument. The next topic, interesting one, and we get more question over here. Okay, that's the topic of the predicate. So you should be able to read the predicate, okay, evaluate like the function. Evaluate it, find the negation of the statement, translate for us, okay? So we give you, you know, at least 3 questions on the predicates. So we have all sort of argument here. So this is going to be, so number 5 is going to be just the optional one that you just use truth table. Okay, truth table. To prove that these are going to be valid argument. Okay, so we go with the number 6. In number 6, this is going to be number 6 is a function type. I'm going to write it down. Okay, this is the number 6. And a statement would be given, x times y equal to the 12, and then there are some questions. Okay, so we can write down the statement. So the statement is the fact that p of x, y, okay, that's a predicate, not equal to each just a statement. Is the fact that the x times y, that's a multiplication notation, is equal to 12. Okay, and you check the domain. The domain are all integers. When you work with the predicate, just consider the domain to make sure that if you want to check whether it's a true or false, so that very much depends on the domain. Okay, so just a domain, have the domain ready. Okay, so then they ask this question. You want to check if the following are going to be true or false. Okay, so this is it. The first part is, so we want to check true or false for the statement. Okay, this is it, statement true or false. So you have to form each statement and tell us which one is it. Okay, so the first part is P of 3 and 4. So you form it first. Okay, 3 and 4 is going to be 3 times 4. This is the way you explain it. It's going to be 12, it's true. Okay, so P of 3 and 4 is true. Or just check it, we accept it. Any question? But write it down, okay? You have to prove it. Don't just say it's true. We want to show how you operate with these formulas. Okay, that's part one. Part two, they ask for the P of 3 and 5. Again, for the statement, so this means 3 times 5 equal to 12, which is wrong. Okay, so P35 is going to be false. Okay, that's part B. Okay, any question? Going to part C. Part C is interesting. Part C, P of 2 comma 6 or P of 3 comma 7. You see, if each predicate is just a proposition, so you can have or connection, or you can have and connection, you can have a negation. So be prepared for it, okay, to read these expressions. So you check to see which what's the truth table of each one of them. So we go with the P of 2, 6. P of 2, 6 means 2 times 6 equal to 12, okay, which is true. Then you check P of 3 and 7. So this means 3 times 7 equal to 12, which is false. Okay, so this is true and this is false. What you have and or connection. You know that. If one of them is true, so the combination or connection is going to be true. So now you conclude that P of 2 comma 6 or P of 3 comma 7 is true. And with that, any question? Is or connection, you know that it's going to be true if at least one of them is true. So you just prove that one of them is going to be true. Okay, question. So that's number 3. And part D. Part D again is interesting, not difficult, but make sure to get it, to read it all right. That's the one. What's part D? You see the part D is for all X and for all Y. For all X and all Y, and this is it. P of XY implies P of YX. You see, that's what you want to know if this is going to be a true statement. Again, you see P of XY means X times Y equal to 12. P of YX means Y times X equal to 12. You know that the multiplication is commutative. So this means if we give me the first one, so you give me the fact that X times Y is equal to 12. So I switch it. That's equivalent to the Y times X to be 12. So this statement is going to be true. Okay. So this is how you explain it. You say that, oh, P of XY is going to be X times Y equal to 12. And that would imply that Y times X is also equal to 12. And the Y times X is what? The Y times X is P of. So we can say that this is it. So if you like, if you give me PXY, I give you PYX all the time. So this statement is going to be true. That for all X and Y, PXY implies PYX. Okay, any question? So that's going to be the true statement. That's part D. Ready for part E? So what's a part E? Part E is that for all X, there is a Y. There is a Y such that PXY is always true. You see, for all x. So this means if I give you an x, you always be able to give me the y such that x times y is equal to 12. You see, that's the idea. So if I give you an x, you always be able to find the y such that x times y is equal to 12. You see, this means I want to translate it for you. This means for all x, there exists a y such that x times y is equal to 12. So this means you should be able to solve this equation for all y if you like. You see, that's one. I give you an x. Can you give me a y such that x times y to be equal to 12 all the time? Any suggestion? Yes or no? True or false?
I think it's false because you could pick an x such that y would have to be a non-integer and the domain is all integers.
Exactly.
So
That's it. Yes. Yeah, because this is what I want just to emphasize. You should look into domain of the function. You see, the domain of the functions are all integers. So you have to give us a number. Okay, you have to pick one number and show that this is not going to be possible. Okay, if you want to reject something, you're going to see it when we get after your test. But it's nice to give us one example. You see, because this said for all x, I can find the y. You say, oh, I give you an x. Give us a number to reject it. Give us one x, an integer, so that you are not going to get a y, which is going to be equal to 12. X and y, both of them must be integer. Okay, number 13. Yes, 13. So I give you the x. So, oh, if x is equal to 13, can you find the y for me? No. I cannot find it because this is going to be 13, y equal to 12. So y would be 12, 13. Is not an integer. Not an integer. Okay, so this means this statement is going to be false. Okay, that's going to be the idea. Even the easiest one is x equal to 0, because you're working with the integers. So if I give you x equal to the 0, it can give me, oh, can you give me a y? Yeah, in that case, you can give me the y. 0 is no good. No, you can't give me the y because we have the 12 here. Because anything times 0 would be 0. It's not going to be equal to 12. Yes, 0 is also an easy example. Okay, for all x, yes, if it was, you know that. If you want to correct it, the domain must be real numbers and not for all x. For all non-zero x. For all non-zero x, there is a y such that x times y is 12. We solve for y. Y would be 12 over x. But we want to make sure that the x is not 0. Okay, so this is going to be false. Any question? So read it carefully. You may have to do similar on the test. And if you want to reject it, just give us a number. You see, in mathematics, if you want to prove something, example is no good. You have to prove it. No example. But you will see when we get after your test, if you want to reject something, one example is enough. Because you can do whatever you like. I say, oh, there you are. This is it. You just take care of this one for me. You see, that's it. That's the idea. So this is the first part, reading the predicate, if you like. Okay, reading it from this information to put them together. Any question? So that's number 6. Number 7 is the better one. We are very much, you know that, we are very much interested in the negation of the predicate. When you want to negate the predicate, we talk about it. You negate the quantifier first. How? For all would be changed into what? Into change there exists. And there exists, the negation of there exists would be changed to all. And if you have a proposition, you just consider the, okay, reverse of that proposition too. Okay, so that's number 6. In number 6, I'm sorry, number 7, yes, number 7, sorry. Number 7. So that's a number 7. This is your number 7 minus 6. This is the one I'm going to talk about it. Okay, the domain is set of all real numbers and we want to negate these statements. So what you need for this problem is this one. The negation of for all x px is what? Is there is an x, not px. And the negation of there exists an x such that px is for all x, not px. So that's all you need. So you change the quantifier, and of course you have to consider the negation of the given proposition. Okay, that's it. The domain of the argument is a set of real numbers in this case. Okay, so this is the domain. Just identify the domain, which is equal to the R, and we go away for one by one. So the first one is there is an X. Just make sure you get the same one. Yes. There is an X and there is an Y such that X is greater than Y. So that's the first one. Okay, this is the way you write it down. You say, oh, the negation of there is an X.
So should that be for all y?
Oh, yes, yes, thank you. Yes. Let's see. Yes, for all Y, thank you. So there is an X for all Y, X greater than Y. You see equivalent to, we change the quantifier, so it's going to be for all X. Okay, for all X, there is a Y. Okay, there is a Y. Now the negation of the X greater than Y. It's going to be the other way around, the complement, X less than equal to 1. That's it. I've seen on the test that the people, they negate the quantifier, but they keep this one. No, you say it's a not PX. Not PX, you negate everything. So that's the first one. Any question? The second one, okay, the second one is, there's a one tricky one in these cases, otherwise the rest are straightforward. Okay, for all y, there is a x such that x squared equal to the y. Okay, so you rewrite it, the negation of for all y. There is an x such that x squared equal to the y equivalent to, for all y would be there is a y. There is a y such that for all x, now the negation of x squared equal to the y would be x squared not equal to y. Okay, so that would be part B. Okay, so nothing special about this. Going to the part C, you can have more than two variables. It doesn't matter. Okay, for part C here. Okay, the part C is that there is a y. Okay, the question is this one. And there is a y. There is a z such that for all x, okay, for all x, x times y is equal to the z. 3 variables. As we go on, you just change quantifiers. Okay, so the negation of there exists a y, there exists a z, such that for all x, x times y is equal to the z would be equivalent to the quantifier there exists y would be for all y. For all z, there is a x such that x times y not equal to the z. Okay, so that would be the negation. Okay, question. Now this is the part D that the people mostly missed it, the conditional one. Okay, make sure you don't miss this one. So let's see what's special about this one. There is an x such that for all y, if y is greater than 0, then x times y is positive. So that's one. You see, this is if P then Q. If P then Q. Make sure you remember the negation of if P then Q. I remind you. You see, this is P. If P then Q, remember the negation is equivalent to, remember the P or Q would be, P then Q was in not P or Q, not P or Q. The negation, the not P would be changed to the P, okay, or would be changed into the not Q. Make sure you know this one, you remember it. You see, that's a negation of the conditional implication. So the rest are going to be just usual. So that's it. I repeat it again. I want to find the negation of there exists an X such that for all Y, if Y is positive, then X times Y would be positive. So this would be equivalent to change the quantifier there exists would be for all X. There exists a Y. Now there you are. P and not Q. So there is a Y such that Y is bigger than 0. You see, Y is bigger than 0. But, remember, but or and negation of this one, X times Y is not greater than 0 means less than or equal to 0. So there is a X, there is a Y such that Y is bigger than 0. But, okay, but this is it. You can, you don't need it, but you can use parentheses such that X times Y is otherwise is less than or equal to the 0. So just for this implication, that's something extra that you have to remember. Otherwise, it's a straightforward problem to get these numbers. And make sure to use a proper symbol for the there exists and for all. Okay, we give you one, the negation, one section of the book. So I'll give you one. Any question? Now, the next two question is a kind of translating again. You got to be careful. We give you something in symbolic form, then we wanted to change it into the English format, okay? And then the other way around. We give some English expressions, okay, word expressions if you like. Some word expression, and then you are going to change it to the, okay, to the symbolic one. So the way sometimes you write these are interesting. Okay, for example, if you want to change something into the everyday life English, you are not going to get that, you are not going to tell us that X is dot, 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 okay? So when you change it, there's going to be an expression. I'm going to tell you what some people will write in this case. The format of the problem, the instruction is very important when you read it. Look at this. Let's see what I'm talking about, and I write it down for you. So look at this, number 5. This is, in your case, this is number 8. You see, this is the one. This is the expression that we have. You see the domain that we consider domain of all penguins. Okay, so let D of X is the predicate that X is dangerous. Okay, X is dangerous, but remember X is coming from the domain. What is the domain? Domain is the penguins. So D of X, whatever X is. So so X is a penguin. So D of X means penguins is dangerous if you like. But it depends how many do you have. This is what we're going to do for this. Now we want to translate the following, okay, quantifier statement into simple everyday life English, everyday English. So for example, the first one, for all X, dx. Any suggestion?
All penguins are dangerous.
Yes, all penguins are dangerous, or every penguin is dangerous. Yes, that's one. Okay, so you are not going to say that all X are dangerous. Some people, they write all X are dangerous, or every X is dangerous. No, when you translate it, X is going to be, in this case, the penguin. Okay, so the first one would be, yes, all penguins are dangerous, or every penguin is dangerous. Okay, the next one, there is XPX.
Some penguins are dangerous.
Yes, some or just one. Yes, some penguins are dangerous, or there is a dangerous penguin. There is a dangerous penguins. Okay, any question? I write it down, so that you can see it. And the next one is a little bit tricky. And this one, remember, when you want to translate, you are not going to change it. How about number C or no? Any suggestion for C?
Not all penguins are dangerous.
No.
Is
As
not the
is,
case
remember.
that there's a dangerous penguin?
Yes, we can do that. Yeah, that's better. Yes, it's not the case that. It's not the case. You see, because we have to translate this not first. Okay, not first. We know that. I've given this one on the test. Some people, they consider the equivalent. They change it first, you see. You know that if you change it, it would be what? It would be for all x and not dx. For all x, not x. But you have to translate it as is. Yes, you can say that safely. It's not the case that there is a dangerous penguin. Or not that, you see, not that there is a dangerous penguin. You see, these two expressions, just don't change it, as is. Okay, and the last one, there is a x, not the x. Any suggestion?
There's a penguin that's not dangerous.
That's it. Yes, that is penguin. Okay, so be careful when you write it down. You know, we make up something regarding this. So I'm going to write down my expressions so that you know what's going to be the case. So this is it. We go with the first part. For all x dx. Okay, this is the way I did it. Every or all, it doesn't matter. I go with this one. Every penguin. Okay, every penguin is dangerous. Or all penguins are dangerous. Okay, just pick the one that you like. Okay, that's it. Dangerous. So that's my indications. The second part was that's the second one that's clear. There is a x px. There is a dangerous penguin. Okay, there is a dangerous penguin. Okay, that's one. The tricky one was this one. Okay, because this negation is outside, you see. The negation is going to be outside of everything. Okay, this is it. So this means, you know, it's not the case or not that, you see, that's it. Not that there is a dangerous. Okay, that's going to be one. Not that there is a dangerous penguin. This is one, or you can say that it's not the case. It's not true. It's not true, or it's not the case. It is not the case that there is a there is a dangerous. There is a dangerous penguin. Okay, this is the one, and the part D.
I'm sorry, on C.
Yeah.
How come we don't do the same thing that we did in 7 for negations and change that into for all x, not dx?
No, because when it's a translation, you are not allowed to change it.
I see. Okay, thank you.
That's the kind of rules of the game. Okay, so then the part D was there exists x, not dx. Okay, and you know that that was correct. That there exists or there exists a penguin. Okay, penguin. That's not dangerous. Not dangerous. Yeah, when I was in England, I was a PhD student. I was, you know, a police interpreter. I mean, they, you know, they need the interpreter. They ask. At that time, there were not many, you know, oversees the students at the university. So they contact my advisors, and I went to the police, and there was a guy, she made a mistake, in the shopping, something happened. So she was arguing all the time with me that, oh, I didn't do it, that was a mistake, that. But that at the end of at the first part of the court, they asked, do you plead guilty or not guilty? So anytime I explain it to her that, you should plead guilty or not guilty, she just repeat the story that, I got some bad news from home, that. And at the end, she convinced that I said, you say plead guilty, then you can explain it. But then I faced the judge and I said after 10 minutes, not guilty. Then the judge just asked me to come to the desk and he said, hey, you have to translate everything for me. You talked to her for 10 minutes and then at the end you said not guilty. Tell me the whole story. So that's one. So the translation must be exactly the same thing. At that time was a very good one, really. I was a student, and at that job they pay you something like 10 pounds at the time. It was $20. And in 1980, 1979, 80, $10 for the students was a very, very good one, because I had only 150 pounds, which is $300 for my scholarship. That was quite lots of money at the time, but not now. Okay, so be careful to translate it correctly. So that's part number 8. Number 8. Now, number 9 is the other way around. This is going to be a little bit more tricky. Okay, the way you are going to translate this one for us. So in this number, this is number 8, on your case. The expression in word forms given, then you want to translate it into symbolic form for us, okay? So the idea is about the movies in the domain of all movies. All movies, Vx predict, it's going to be no. It's the predicate that the X is violent, okay? So write the following statement in symbols of the predicate logics, okay? So you got to be careful. You can only use, the X as your kind of movies, and then the V of X would stand how violent these movies is or are going to be. Okay, do you want to try the first one? Some movies are violent.
There exists an X, V of X.
That's it. There is a X, Vx. There is a X, Vx that would give us everything we need. Okay, that's a symbolic form. We talk about the sum, it's just that there exists. Okay, so there is a X, Vx. I'm going to write down at the end. Let's try all of them. Then we get the other one. Okay, the second part. Some movies are not violent.
There's an X, not VX.
That's it, yes. Some, again, we start with the sum. There is a X. There is a X, not Vx. Yes, that's correct. Part C, no movies. No movies are going to be violent. You have, you have a couple of choices for this one.
For all X, not VX.
Yes, this is one way to do it for all X and not Vx, or you can use the other expression that we have. It's like not that there is a violent movie. I use this one. The negation of there is X, Vx, which is the same for all X, not Vx. Okay, and the last one is easy. All movies.
For all X, VX.
That's it, yes. So I just give you the idea, and this is going to be the case, okay? So the people, they usually write this one. They have only one doubt about that part of, kind of, it's not the case or not, but otherwise, this is one of those easy questions. So we go with the first one. So the first one was, this is it. Some movies we talk about is going to be there is a X, there is a XVX. Some movies, or there is some movies violence. The second part. Some are not. So some, there is the X, not Vx. Okay, that's the one. And for part C, for part C, we have two different choices. X, we can go with the all X, and not Vx. This is one. Or the one that I have is this one. Not that, not that. There is a XVX. Okay, it's the same thing. Because if you change it, you get exactly the same one. Okay, and the same meaning. And the part D is clear. The part D for all X. For all X, Vx. Okay, so be ready for it. So the implication, this type of argument are going to be very important really of this part of that chapter, because you're going to use it in future. And we use it right away when we get to this method of proofs that we have. Okay, so these are going to be the predicate. Any question? Now one more question, and that is method of proofs. We are going to have quite a lot of method of proofs, but we talk about one of them. That was a direct proof, okay? A direct proof means you just prove it as is, okay? You don't have any other. So we are not going to worry about it that you are going to make a mistake or confused. No, you're not going to be confused because we don't have anything else. Okay, so this is it. You have to use a couple of definitions that we have, put them together mathematically, and carry on your proof. So it's going to be all about odd and even numbers. And so we want to prove the first part. For example, the first part, we want to prove that the product of two odd integers is odd. The product of two odd integers is odd. Remember, you cannot give us an example. I've seen some people that give us example, say, oh, 3 times 5 is 15. Yes, that's one example. You have to prove it. So direct proof, you pick two odd numbers. So this is it, the proof. Say suppose m and n, x and y, whatever you like. Suppose m and n are odd integers. We have a definition for the odd. Remember, a number is odd if it's a form of 2k plus 1. So for the first part, so definition, there is a k such that m is equal to the 2k plus 1. That's the definition of odd numbers. But since you have the n, you want to apply the n too, so you are going to call this one k1. Remember, if you're just using one number, it's k. But it's more than one, of course, you have to have different k. There's a k2 such that n is equal to the 2k2 plus 1. That's a step one, which is very crucial. If you don't use the same k, you are out. They are different numbers, remember. Now check to see what you want. Sum, product, the difference. Okay, these are one of the options. In this case, the product. Multiply them together. Multiply them together, show that the result is also of the form of 2k plus 1. There you are, m times n. 2k plus 1 times 2k2 plus 1. Foil it. There is nothing obvious. Don't say it's obvious. No, it's not. We have to prove it. Foil, multiply, go forward. 4k1, k2, 2k1, 2k2, and 1. Algebra. You have to change it into form of the 2k plus 1. We talk about it. You see, look at these. So what you can do, you need a factor of 2. So take the 2 as a factor here. So it's going to be equal to, you factor out the 2, the leftover is going to be what? 2k1, k2, k1, k2. You leave the 1 as is. Now these are all integers. Adding, subtracting, multiplying the integers are going to be integers. So we're going to call everything here a k. So that gives you 2k plus 1. So what you did, you prove that there is an integer k such that m times n is equal to the 2k plus 1. So m times n is odd. You see, nice. And logic descended proof. This is the proof. Maybe we're going to write it down for us, okay? So put your definitions because this is all you have. You have your definitions of the odd numbers. These are the odd numbers. Then the algebra. You want to multiply. But remember, you have to get back to the 2k plus 1. So you may need to know to do the factoring here to be able to take care of it. Okay, that's going to be the first one. Any question? The second part is it the sum of two odd numbers is even? You add them together. If you add them together, okay, any questions? Give you quickly the second part. So we don't have anything, you know, complicated for the time being, and there is not going to be complicated thing at all, because the way you write is important for us. Be precise, okay? That's one. So the second part, you want to prove the sum of odd, in this case is odd, yes, the sum of any two odd numbers is what is even. Again, pick two odd numbers. Suppose m and n are odd numbers. Definition of the odd. We go with the k1 and the k2 because we have the 2 to 1. There's the k1, m is 2k1 plus 1. There's the k2, n is 2k2 plus 1. What do you want? Sum. Add them together. So, oh, note that. What I have now, I need the sum. So add them together. 2k1 plus 1 added to 2k2 plus 1. Remember what you are looking for. You are looking for at 2k plus 1. Oh, you want to prove that it's even. You need a 2k. So 1 and 1 would be 2. Combine the like terms. It's going to be 2k1. 2k2, 2. Since you need a 2k, factor out the 2 in this case. 2 out, k1, k2, 1. They are all integers. Call it k. So what you have, you prove that m plus n equal to the 2k. That's it, it's even. So you say, oh, I find the k such that m plus n is 2k. So m plus n is even. And you're done. That's a proof of this. Any question? So again, you're writing your method of proof. You just check to see how you explain it, how you bring the definition of the odd, definition of the even, because these are the only thing that we have. Okay, and try to give it the last one too. The last one is you want to prove that you get several of these type of problems in your book. So I just give one to make sure you know how to write it down. If n is odd, okay, then you want to prove that 5 n squared plus 7 is even. Okay. Again, don't give me example. Don't say that, oh, n equal to 3. 3 squared is what? 9. 4 times 9. 45. 45 plus 7. 52 even. You get 0. Just give us an example. The proof is a general proof. Okay. So that's a difference. Again, let's start with the n. N is odd. What does it mean? Solution. N is odd. So definition of the odd. There is a k. You don't need the k1 and the k2 because it's just one number. There is a case such that what n is equal to the 2k plus 1. What do you want? 5n squared plus 7. Bring it in. Note that. What is 5n squared plus 7? Substitute. You have to substitute, show that this is of the form of the 2k. Okay? Carefully operate the algebra. 2k plus 1 all square plus 7. You have to go on because you need to prove there's a 2k. So FOIL or a square of the binomial. 2k plus 1 times 2k plus 1, or the square of the first one is a 4k squared. You multiply these three numbers together. 2 times 2, 4, 4k. And the square of the 1, which is 1. Or FOIL method, whichever you feel comfortable. Distribute 20k squared, 20k, 5 and 7. Combine the like terms, 20k squared, 20k, 12. What do you want? You want of the form of the 2k, pull out the 2. 2 as a factor left over. 10k squared, 10k and the 6. They are all integer. You cannot call them k because you already used the k. So you may call them k1. Or call it t, it doesn't matter. You get 2k1. That's it. So what you proved? You proved that, oh, there is a k1 such that 5n squared plus 7 is of the form of the multiple of 2. So 5n squared plus 7 is even. Nice, you see? You proved it. So when you get the idea, it doesn't matter really, whatever they give you. You just write it down nicely. The order of the proof, you'll be able to do it. Give me one question on this one, maybe 2 parts. But it's going to be related to this type of ideas, okay? Make sure to write it down precisely, okay? And there are proofs, so no examples. You have to prove it right away. That's it. Any question? So study your quiz, and whatever I did today, really, you should be fine. Okay, for the test on Wednesday. We give all the lecture hour, but make sure you're not late. Just make sure you get enough time to finish it. Any question? So study your quiz. If any question, you know, please.
Yeah, Professor.
Yes.
On the syllabus for the homework list, there's 3.3. Do we do that even though we didn't go over that in class?
I checked that, but I think it should be fine.
So we do 3.3.
I should check to see what is 3.3. 3.3 is 3.1. Yeah, whatever it is on that list, you should be able to do it.
Okay.
Yes, some section I just combine them together, but I checked that one. I checked to make sure that we cover it, because that's from the last semester. But everything on that one is going to should be fine. But I check to make sure that you have no difficulty. But you know that we don't collect any assignment on Wednesday. The assignment would be collected on your next quiz, which is going to be in 2 weeks' times. So for this test, you just concentrate on your review. Okay, I'll check that one and let you know. Okay, have a good one. I have to go. I have a class at the university in person. See you on Wednesday. Bye-bye.
Thanks. See you Wednesday.
Thanks, Professor.